Hello guys, it's Miss Williams again. Hopefully before this one, you know that you're on day 3 of the lectures for this week and that you hopefully watched earthquakes before this lecture. If not, please stop what you're doing and go back and do that first. Alright, so for volcanoes, I'm recording this on Tuesday, but tomorrow we're supposed to get some not favorable weather. Unless you love snow, then it's very favorable. But if I end up not being able to come to the schoolhouse tomorrow, I won't be able to do this cool thing that I want to do. But if I do have the opportunity to come to school tomorrow, because, weather, I may be able to pull off a little surprise. So, be on the lookout for an additional video. I'll label it as watch this cool thing or something like that. If not, if it doesn't show up, that means I wasn't able to come to school. But that's a possibility. So, we'll see what happens. Anyways, we are going to talk about volcanoes. I love talking about volcanoes. Let me tell you, I took a whole volcanology class. I did a huge paper on Mount Vesuvius, and I love volcanoes. They're so fascinating. They are always changing. They can wipe out entire cities. They can be weird. Like some volcanoes, like they have black lava. Sometimes volcanoes can pop up overnight. They all look very different. They have all these types of different explosions. I could talk about volcanoes for forever. But for your sake, I'm going to try to keep it a semi-short lecture. I will probably post a cool video for you to look at for some of the cool volcanoes, because there's even volcanoes that are already, the lava is on fire. It's like a blue flame. And yeah, so volcanoes are super cool. Yeah. I just love them. Anyways, volcanoes. I'm going to go ahead and start this presentation. Hopefully you already have your split screen up. Me lecturing with PowerPoint on one side, and then your Google Doc on the other that you are going to be filling in by a keyboard. I have a little keyboard here. All that fun stuff. So, volcanoes. Again, they're awesome. They're very deadly. I mean, a lot of volcanic eruptions probably wiped out several different animals and, just killed a lot of humans. Pompeii, which is a city right outside of Mount Vesuvius that I mentioned earlier. So very deadly, but very fascinating. So a volcano is just an opening in Earth's crust through which molten rock, gases, and ash erupt. This is also the landform that develops around the opening. So it's not just the lava, magma aspect of it. It's also all the land that forms around it from the cooling lava. So it's the whole structure, not just the inside part. Alright, so why volcanoes form? There's a couple of different reasons why volcanoes can form. The first is because of volcanic eruptions. So this occurs whenever magma rises to the surface. So again, it's magma because it's below the surface. So it rises to the surface, and then it comes out. So this happens whenever the asthenosphere melts enough to flow. And then 3 things can cause this. A decrease in pressure, because temperature and pressure is very important whenever we're talking about magma, because it determines how much of a liquid it is and if it's solid and all of these different aspects. So a decrease in pressure, which would be something like what happens at a mid-ocean ridge or a rift valley. So at a divergent plate boundary, whenever the things come apart, there's not all that pressure on top of the magma, and then that magma will come up in between the plates and come out like it would in a volcano. Another reason why volcanoes could form is an increase in temperature. So kind of like a hot spot. So whenever the plates are moving over the asthenosphere, some parts of the plate are thinner than others. So these thinner parts, kind of like where Hawaii is, that thin part of the plate moves over this hot spot in the asthenosphere. So since that plate is thinner, that hot spot's going to melt that thinner part of the plate and then most likely cause a volcano. And this is how island archipelagos are formed, because as the plate moves, because the plate's always moving, the hot spot doesn't move. So, you have your first little island here, and then as the plate moves, there's an island here and here. And if you look at the shape of island arcs or archipelagos, you can see how that plate was moving over the hotspot. So hotspots do not move itself. The plate on top of the hotspot moves. And then an increase in the amount of water in the asthenosphere. So in one area for our convergent plate boundaries, whenever they go like this, at our subduction zones, that plate that's going underneath, there's a lot of water trapped in this rock here. So this rock has a lot of water, and as it goes underneath here and gets pushed down into the asthenosphere and begins to melt, all that water burns off and comes up. And it creates very volatile gases, which means they're very high energy and very hot. So normally this is where you get some more explosive stuff happening, because all that water is burning off of the rock that's going into the asthenosphere, or the magma/mantle. All right, so where do volcanoes form? 3 spots again: divergent plate boundaries, which is a decrease in pressure, convergent plate boundaries that have subduction zones, and then hotspots. So volcanoes at divergent boundaries. This is due to a decrease in pressure as the plates pull apart and let magma rise up. These are also called, especially on land, fissure volcanoes. So, of course, we have them in the Mid-Atlantic Ridge underneath the water. Then we also have them in in the Great African Rift Valley. But some fissure volcanoes that aren't listed on here are also up in Iceland. So those are actually really cool as well. So here, again, the Great Rift Valley, as the continent's being pulled apart, we've got the magma coming up, and you're getting these different forms. So this is something that you may see like in Iceland. Yeah, Iceland or Greenland, one of the two. It's literally just open cracks in the plate where the magma is able to come up. So the next type is at a convergent boundary, most likely at a subduction zone. A subduction increases the amount of water in the asthenosphere, which lowers the melting temperature. So as the denser ocean crust is pushed lower, it melts into magma. So whenever continental and oceanic plates converge, a volcano forms on the land, as you can see here. We've got this oceanic plate coming down underneath. We've got all the water and magma coming up. And then we get the volcanoes on land, because at this point, this plate is up underneath the continental plate. So anything that comes up off of it is going to come up and show the features on this continental plate. But then again, you can also have some islands and stuff like that. So again, one example of this is Mount St. Helens. And then we also have this one volcano in Indonesia. I'm not going to try to pronounce that. We all know I'm not good with words. You can just read it and take it as it is. So the next type of volcano is going to be from hotspots. This is whenever volcanoes occur at places that aren't plate boundaries. So again, like I said earlier, it's going to be at a thinner spot in the plate. Not necessarily at the boundary, but anywhere within the plate that's thin enough for these hotter spots or the asthenosphere to come up through. So we call these hotspots. Hotspots are areas where hot magma rises from deep in the Earth's mantle, and then magma escapes where the crust is the thinnest or the weakest. So we've got this one part of the mantle that's super hot and it's pushing up this stuff. And then whenever this weak spot of the plate comes up over it, that's whenever you get volcanoes. So it starts out solid and it melts whenever the weakest part gets to that increase in temperature. One example of a major hotspot is all the volcanoes that make up the islands of Hawaii. So, like I said, you get all the different islands because the plate is moving over this one hotspot, and that whole plate is weaker where those islands appear. So now that we've kind of talked about where volcanoes occur and why they occur, let's look at the 4 different types. So like I said earlier, there's so much stuff I could talk about for volcanoes, but the first type of volcano that we're going to talk about is the shield volcano. So shield volcanoes form from runny lava, so this is a low viscosity, and it tends to flow along distances before hardening. So this is a lava that like comes out really fast, moves really fast, and spreads out everywhere. So this volcano has a broad base and it's gently sloping. It's normally less explosive on its eruption, so it's more like the lava just comes out and flows and goes. And then the type of magma that it has is normally mafic basalt, so black, runny lava. And this volcano itself is made up of layers. So these are some of the bigger volcanoes that you will see in Hawaii. You've got the lava just kind of flowing out, hardens, flows out on top of that, hardens, and you just get layer after layer. So one example in Hawaii is going to be Mauna Loa. I think that's how you say it. Don't hold me to it. Here's just kind of a breakdown. You can see all the layers building up and up. So here's the central vent. You don't necessarily have to have lava coming up from the top. It can escape through weaker points in the sides. And as you can tell in this bottom picture, these are huge. Like, they may not be the tallest volcano, but they cover the greatest amount of land horizontally because these big lava flows just keep going and going. So it's a very wide volcano, but it may not be the tallest. The next type of volcano is going to be a cinder cone. So these are more of your tall ones. These form whenever molten lava is thrown into the air from a vent. So as it falls, it breaks into fragments called ash or tephra that harden before hitting the ground. So the ash and tephra make up a cone-shaped mound. So instead of having the lava flows go out and build layer on layer, you're going to have bigger, more explosive eruptions with thicker magma. And as that magma is thrown into the air, it cools into rocks. And as those rocks fall, the rocks and ash, they pile up like that. So, like I said, more explosive eruption, magma is thicker, and it's normally made up of felsic rhyolite, so lighter colored igneous rocks. One good example of this is Krakatoa in Indonesia. Again, you can see all the ash and rocks just piling up and up. So its base isn't normally necessarily as wide as a shield volcano, and it's normally a little taller. And here's some more cinder cones. We've got some in New Guinea and again in Iceland. As you can see, it looks very different. This looks more like your typical volcano that you would like make out of Play-Doh or whatever you make volcanoes out of. But it's just the layers of ash and rock built up instead of the big lava flows going out and cooling. So the next one, you can call it two different things. One, you can either call it a composite or a stratovolcano. So this type of volcano has alternating eruptions between something more like a shield volcano and then more like a cinder cone. So it kind of alternates. So it's built up by ash and tephra, but also because of lava layers. This is going to be your most common type of volcano. It's normally a medium color just because, it switches back and forth in eruption type. It's normally moderately sized. Again, volcanoes can be very different in sizes. But most common, made up of layers of ash and tephra and lava. So like one explosion will have very thick lava and be very explosive. So you'll get the ash and tephra. And then the next eruption will most likely be more calm and just have the large lava flows. All right. So one example of a composite or stratovolcano is going to be Mount Pinatubo in the Philippines. So, of course, you've got the huge explosions that you would have in a cinder cone cinder cone volcano. And then you've also got the lava flows that just kind of happen more gradually. So this honestly, the type of eruption style depends on how much gas is caught up inside of the magma chamber. Because normally you will have a more cinder cone style explosion, which is very explosive. You get these large clouds and lots of ash and tephra. That's going to be caused by a buildup of gas within the magma chamber. So if the gas is trapped down in here, it's going to get to the point to where the rock cannot keep it in there. So then the top's going to blow. The top blows whenever you have a large explosion like this or an eruption. On the other hand, if gas isn't building up inside the magma chamber and it's gradually escaping, you will just most likely have the larger lava flows. So here's just another image of a composite volcano. As you can see, it's kind of wider at the bottom, like a shield volcano would be, but it's still getting the height of a composite volcano. And the next one is a fissure volcano. This is where fissure volcanoes form in long cracks where the plates are pulled apart near other volcanoes where the crust is weakened. So these could be near cinder cone or shield volcanoes. It could be around those, or it could just be where the plates are pulling apart. Let's see. Where were you at in the notes? Fissure volcanoes. Okay, so those are the 4 types of volcanoes. But as an American, there's also something else that we've heard of that could possibly be a supervolcano. It's clearly not any of the 4 type that we've seen here, but it's a little different. So Yellowstone. We've seen and heard of movies about Yellowstone and documentaries, and, Yellowstone is potentially, at some point, a threat. How big of one, we don't know. But Yellowstone has a large caldera. And what a caldera is it's almost like a magma chamber within a volcano, but it's completely underground. So there's not like a typical, here's a big volcano, whatever. It's just a big magma stockpile under the ground. So we have been able to study the different lava flows of Yellowstone. As you can see here, let's see. The oldest lava flow that we've looked at from Yellowstone is the Huckleberry Ridge. So it's this large. And that was about 2.1 million years ago. And then about 1.3 million years ago, we had a very smaller lava flow. But then even closer in time than that, we had about 0.64 million years ago, we had the biggest lava flow. So the production of magma from this caldera changes, it varies. So what happens is a volcano's pressure starts to build up. The volcano releases large amounts of lava, and as the lava is released, the pressure decreases and the volcanic mountain begins to collapse. So at some point in geologic history, over a good portion of the entire Yellowstone National Park or whatever, there once was a volcano. It blew up, and then the volcano kind of sunk, and it became more flat of what we see today. We still have, the hot springs and the vents and the geysers and stuff like that, but we don't really see the external shape of a volcano. But the magma chamber is still there. It's below the ground, as you can see in these pictures. Now, this isn't necessarily a good picture of Yellowstone. This would be a good example of Crater Lake out in Oregon. Oh, yeah, which is actually what's next. So, Crater Lake in Oregon should actually be called Caldera Lake, because this is not a crater. At some point in geologic history, this whole thing was a big volcano. It was most likely a cinder cone, maybe a composite stratovolcano. I would have to look at the rocks or look up the different rock layers. But this was not made by a meteorite or anything. It was a large volcano that had the top blown off. So once the top was blown off, and then it kind of sunk back in, being a decompression in the geography, water starts to build up there. So that's where you get the lake from. But then if you look closer, there's like a mini volcano in it. So that's just letting you know that the magma chamber below this lake is still active. So that means this was a little mini volcano that would start to build up and build up. This is clearly a cinder cone. As you can tell, it's very tall and the base isn't as wide. It looks like the tephra and ash has just been layering up. So this is still active. Like if you go to Crater Lake now, I think you can swim in here. I don't know if many people do, but whatever's happening, you can see like smoke and stuff coming out of this little volcano. It is still very active. That's because the magma chamber, although it may not be as large, is still active underneath. And that kind of goes with the same for Yellowstone. That magma chamber, the caldera, is still active underneath the ground. So in your notes, you can do this. You don't have to do this if you don't want to. It may help you. I would label the different parts of this. So clearly this is your main vent or your crater. Here's a secondary vent. An vent is just an opening to where gas and magma and lava can escape. So again, magma chambers down here. Magma is underground. It's not been exposed yet. Lava is out here. It's already reached the surface. Ash and dust. It's not just gas. There's actual particles. These are your tephra bombs. So tephra is just like the larger particles that come out of an explosion. And then, of course, the whole structure here is your cone. So like I said, you can draw this in there and label it. If not, you just need to kind of know what these things are. And this is just a cool, it's most likely from either a lava flow from a shield volcano. Most likely, that's what I think it is. And what's happening is that lava flow is coming over the edge of the coastline there and going straight into the water. So as soon as it touches the water, it starts to harden. So you get all this steam and you get some cool features going on there. This is just a pretty picture, most likely up in Iceland. You've got your fissure volcanoes, and then you've got the northern lights. Nothing too crazy, I just thought it was pretty. But yeah, so again, volcanoes. I could talk for forever about volcanoes, but we don't have that type of time. Maybe I'll revisit volcanoes after SOL testing, but there is your lecture on volcanoes. You've got the why and where, you've got the 4 types, you've got examples, and we've also discussed, what formations occur because of each type of volcano. If you have questions, email me. Hopefully, if any of you love volcanoes as much as I do, we can have more conversation about this. If not, that's fine. This will be my last recorded lecture, I believe, before break. So I hope y'all have a very Merry Christmas. And if you need anything, please just email me. It doesn't have to be schoolwork related. Like if you're just like, I need a vent, or like Miss Williams, I need like an encouraging quote. I don't care. Email me. I will most likely respond. If not, I'll respond to you when I can. But yeah. Bye, guys.